So, what you're going to learn today is what a vector is. You'll understand the different vector direction conventions, and you'll be able to draw, at the end of the day, you'll be able to draw a scale drawing of a vector. So, based on what you see on the screen, and what you maybe heard or what have you, what do you think a vector is?
An arrow.
An arrow? Okay. I will say something with dimension or direction, maybe, Jaden? Is that what you meant to say, or? No. Okay. Two directions.
Something like that, because doesn't that the guy super villain from like Despicable Me names vector, and then he's like,
Hold on to that thought.
he says exactly what it meant.
Hold on to that thought, Hody. Okay. I will say this. Vectors are sort of one of the building blocks of physics. It is not a little sort of like 2 or 3 day unit, 2 or 3 day sort of lesson, and then you can forget about it, okay? Vectors literally are going to be in every part of, almost every unit's going to involve vectors in some way, okay? It's kind of like me teaching you how to add. It's kind of that important to physics, okay? So keep that in mind, and it's sort of one of those sort of building blocks, sort of major kind of concepts that's going to last throughout the whole thing. Okay, so you have a handout in front of you, right? Notes, if you will, and you're just going to fill in bits and pieces as we go. Okay, let's give it. So, it's kind of a cop-out. A vector is simply an arrow that represents a vector quantity.
Yeah,
You should. Okay, so a bit of a cop-out, really. A vector is simply an arrow that represents a vector quantity. You could even say it's a scientific model, because you can't really see a vector quantity, so the arrow is the model for that. It's our way of describing it, kind of, right? Okay, so what's a vector quantity, Mr. Matt? You didn't really say a whole lot, right? So a vector quantity is, oh, hang on. The length of the arrow represents the magnitude or the size of the vector. The length of the arrow represents the magnitude or size. Quite often I get kids asking me, what is the word magnitude, Mr. Bennett? And, well, it means the size. And the direction that the arrow points represents the direction of the vector quantity. So it's our way of describing this vector quantity that I still haven't told you about. Okay.
Hey.
I call.
I'm applying for a new film loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah.
At this point, I'm the only person in the movie theater laughing. I have my children with me. They're a little bit younger. When did this come out after?
I think it was 09.
It's been a while, right? Kids were a little younger, so we went to see it. And I am laughing because the supervillain is named Vector, and he's committing crimes of both size and magnitude. And I'm the only one that gets it. Now, you do too.
I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranhathon! Oh yes! Finest live piranhas ever seen one before. Now you have 9 times bigger. You want a demonstration? Oh! Sometimes pick piranha.
Hey, go away. Oh, and it was recorded too. So a vector has what two things out of it? Direction and magnitude. You got to finish it with a. Oh yeah. Vector quantities are quantities that have a direction associated with them. They have size and direction. Magnitude and direction associated with them. Oh yeah. Will you remember it now for the rest of your life? Sadly, yes. That is my job. No, no you won't. Vector quantities are quantities that have a magnitude and direction associated with them. Here are some common examples. I call them the big four. They are displacement, velocity, acceleration, and force. All of those are vector quantities. Why? Because they have a magnitude and direction. When you talk about displacement, you talk about maybe taking 10 steps to the right, or 8 steps east, or something along those lines. Right? Velocity, you might be flying in an airplane at 300 kilometers an hour southwest. Direction. Acceleration, you're falling towards the sky after you jump out of an airplane at minus 9.8 meters per second squared. Down. Falling from the sky. Out of the sky. Force, I might come over and smack you with 550 newtons of force. I wouldn't do that. 50 newtons towards your head, I guess, would be the direction. Anything that you can put a direction behind and it makes sense, that is a vector. The opposite of vectors are scalars. The opposite of vectors are scalars. I think you should have a spot there, don't you? Oh. Oh. It's always like the next one, scalar. Scalars are quantities that do not have a direction associated with them. Examples are mass and time, right? If I jump on a scale and it shows that I weigh 80 kilos, you're not going to be like 80 kilos south. Does that make sense? Right? It took those students 18 minutes east to come get the computers. Doesn't make sense. I did not roast them. It was more of a baking. What's the difference between roasting and baking, really? Okay, so the point is that vectors are there in sports. Vectors also are huge in computer graphics. You know how some... Josh, what are you doing with that laptop? Sorry? It's just open. Mr. Burnett's was looking for that. Vectors are huge in computer graphics because you know how some are really pixelated, like when you blow them up, they kind of look all fuzzy, pixelated, I think. But a vector graphic, actually, when you blow it up, looks just fine. All right, and I'm not going to get into the science behind that, but that's another example where vectors are. Okay, so now, do you guys know how these work? I think you do. And the question is, to start, there we go. Yeah? Okay, I think we're good. Can you answer? Yes? Okay, excellent. So the question is, which of the following properties in physics do you think is a vector? Now I gave you the big four. You know what a vector is. So now you need to pick the one that you think is also a vector. Is it speed, density, momentum, or volume? Knowing what you know, what a vector is. It has a direction. Oh my God. The opposite of a vector is a scalar. So which of the following properties in physics do you think is a scalar? 3 of them are vectors. One is a scalar. Which one is a scalar? Gravitational field strength, density, magnetic field strength, or torque?
How do you know this question?
Excellent. Punch it in. If you've been following along, it should be very simple. Correct answer is B. Well done. In fact, is it not one of those ones?
I knew that you made it obvious. Yeah, you did.
Okay. So, vectors are represented algebraically by a variable, by a letter, with an arrow over it, such as this one for velocity. So we always write, quite often we write the letter of the quantity, like V for velocity, A for acceleration, F for force. Do you have to write something down here, Brady?
You have to draw.
Follow along, man. I really suggest the use of a table. Yeah, it's worked real well for you. You will notice that the vector has an arrow on top of it. When you're drawing them by hand, you can just put a half an arrowhead. Most people do it that way. In the good old days before sort of desktop publishing, they quite often just put them as bold and italics. So if you got a really old book, you might see that. But for the most part, you're going to see them with an arrow top. Okay, now, key point here. When representing a vector graphically, you can move the vector any way you like, as long as the length and the direction in which it points remains the same. Key words there are that the length and the direction in which it points remain the same. Okay? For example, the two vectors shown below are considered equal, even though they do not have the same starting point. So these two vectors here are considered to be equal. How come? They're the same length, and they point in the same direction. See that there? Okay, so they are equal to each other. It's really no different than me doing this. Right? One is black, one is red, one is a little bit different, but they both represent the value 2. In fact, one could even argue that our numbers are simply a scientific model. A model. Okay, now, lots of students ask about the units. What units do I use, Mr. Nett? Vectors are not something that have their own unit. Vectors are a category of quantities. Okay? So the unit of the magnitude of a vector depends on the type of vector you're representing. For example, displacement vector would be measured in meters, or kilometers, or feet, or inches, or centimeters, or millimeters, or decameters, or whatever. Some unit of distance. Velocity vector would be measured in meters per second, or kilometers per hour, or something like that. Force vectors measured in newtons, and so on. So there is no one unit for vectors. Vectors are a category. All right. So we've talked about the units. We've talked about the size. Now we're going to talk about direction. So direction is actually a big part. There's lots of different conventions or ways to express direction, and I'm going to give you a bunch of them right now, and you're responsible for knowing all of them. The first one's easy. So, vector direction. The direction of a vector can be measured more than one way. For example, a man is following a scavenger hunt, and he walks plus 35 meters, 35, and then backwards 10. What is his displacement?
25.
What's his distance traveled? You can use that one that Josh has there. He's not even good. Okay.
Distance is 45.
Distance is 45, displacement is 25. Right, you are. In the middle of something. That's one way to express direction that you already know, right? I'm just reminding you. To the right, positive, to the left, negative. Okay, there are other more complicated ways. An airplane is traveling at 200 kilometers an hour at 40 degrees south of east. Now, before we begin, let's just remind ourselves, north, east, south, west. Someone say it, come on. Thank you. Never eat soggy wieners. Right? Now, for some reason, all my years, every kid, 99% of kids, north, south, no problem. But east and west, it's like 25% of the time they get it backwards. I don't know why. West to the left, east to the right. Okay, 40 degrees south of east. So in other words, I look which way first? East. Oh, by the way, clicker question coming up next screen. If you're not listening, you're not going to know how to do it. 40 degrees south of east. So look east, Kaylee, and then go right you are. So we're looking east, and then we go how far south?
40 degrees.
40 degrees.
So basically you're going southeast.
40 degrees south of east. If I just say southeast, then that means exactly 45 degrees.
Wow.
If you say south-southeast, it means 30 degrees. Or sorry, no, it's 22 and a half. South-southeast would be like this.
Okay, so it's
You don't, you just use a number. 40 degrees south of east. Now there's another way to say that, and that's written right here. It's east 40 south. Most students prefer this way to write it, but you got to be able to handle both. East 40 south. Look east, go 40 degrees south. 40 degrees south of east. You almost got to start at the back here and kind of go backwards. East, go to south, 40 degrees. Okay? Yeah? Nod? Clicker question coming. If you've been tuning out and haven't listening, you're not going to be able to do it. That's a 45 right there. This is 40. Which of these arrows show the direction 30 degrees north of east? If you didn't get it right, 30 degrees north of east. Look east first. Look east, go 30 degrees to the north, like so. What would this one be?
80
This would be, yes, 30 degrees east of north, backwards. Okay? All right, last method. The last method of showing direction. A sailboat is moving at a bearing of 210 degrees. This method assumes 0, 0, 0 is north and revolves clockwise. Okay, so first of all, before I get into that, if you're flying a plane, if you're an air traffic controller, and you got to say, okay, I want you to take, you're the air traffic controller, you're going to say, I want you to go 70 degrees west of south, and the pilot's going to go, oh, too late, crashed, right? There's got to be a better method, a sort of a simpler one that sort of is universal, and that's what this one is. Most pilots, most navigators will use this method. So it's assuming that 0, 0, 0 is north and revolves clockwise. So let's draw the crosshairs again. And what goes at the top? 0. And east is going to be 90. And south is 180. And west is 270. Ready to jot this down? Okay. So a bearing of 210. Bearing of 210 would be which direction? Straight west? Southwest. Southwest. So in fact it would be like this right here, right? This angle here would be 210 degrees. Right? From 0 all the way around 210 degrees. If I had to express this in that sort of east of south kind of thing, how would you describe it? How would I convert this number, the 210, like to this style? What would it be? Like, okay, well, let me ask you this question. How big is this angle right here? Just this little one. 30 degrees, right? So we would say it would be south 30 west, right? South 30 degrees to the west. Right, Shade? Good? Okay, now, here's a little bit of trivia here for you, because I'm all about that trivia kind of stuff. When you're flying a plane, you're landing on a runway, all the runways are always named. So if you were landing and you were facing south 30 degrees west, you would be landing on runway 21.
21.
210.
Okay.
The runways are every 10 degrees, so the runway pointing this way would be exactly, or would be numbered 210, or sorry, 21. Now, runways can go point either direction, right? You can land either way. So if you were going the other way, what runway would it be numbered?
3.
How'd you get 3, Teague?
Because it's just near the traffic.
It's right over here, right?
Okay.
It'd be like a whole 180.
Yeah.
Would you take 210 and subtract 180?
Yeah.
And you'd get 30. Okay, so the runways, when next time you are out on an airplane or whatever and you have a look out the window, you should see a big number. Based on that, you should be able to tell what direction you're facing. And then everyone will yell at you, nerd. But that's okay. Hey, guess what's coming up next? Which vector is at 300? Bearing 300. I'll use those square brackets to signify that. Okay, correct answer is D. Yay! Most people got it right. 300, because straight west is 270, right? Okay? So this would be 30 degrees. How would I write this the other way? How would I write this the other way? No. The south of east method. This would be 30 degrees north of west, right? To the north of west. Okay? Okay, now, here's the doing part where you guys are actually going to do. You're going to draw right away. You need about 3 minutes to explain this, and then you're going to try. Scale drawings are often used to represent vectors graphically. For example, a vector of 300 newtons east could be shown as, okay? So, I'm going to draw this. I need a ruler and a protractor. If you don't have one, you need to get one. I have a few protractors that you can cut out here. And I have some rulers. The protractors are in here. If you cut one out, you can just keep Okay, so it's 300 newtons east. Watch out for the N. N does not always mean north. The N in this case means newtons. Now, the first thing you have to do when you draw a scale drawing is make a scale. Your scale always, I say it 3 times for emphasis, starts with 1 centimeter equal. The thing that comes to the left on an equal sign like that means on this piece of paper, 1 centimeter equals. So you always start with 1 centimeter. Always! Why do you think I'm emphasizing this? Because I've seen it over 25 years that people screw this up. So don't. It's always 1 centimeter. It's the rule. So we're going to say 1 centimeter equals, and then you get to pick. You could say 1 centimeter equals 10 newtons. Then your line would have to be long. How long? 30. You could say 1 centimeter equals 20 newtons, and then it would be 150. But let's make it something a little bit more reasonable. How about we say 1 centimeter equals 100, or let's go 50. You always want your vectors to be in that sort of 3, 4, 5, up to about 14 centimeters long. After that, they're too big for the page, and if they're too small, you get too much error. So 1 centimeter equals 50 newtons. You have to have that. You have to have that. You have to have that. Okay, now we're going east. Now, so that I know where you're measuring from, you should always draw what I call a reference line. Okay? I'm going to draw my reference line straight up and down, and I'm going to label that direction as north. Doesn't have to be very long, just a little tiny one. That is where I measure from when I'm checking yours. North. We're going east, so you get your protractor. Okay, you get your protractor, and you put it so that 0 is north, and you mark it, put it on there. I always go from the bottom of my reference line, so like so. Either one, really, right? And east is going to be at 9 degrees, so you make a little mark like this, right? Get rid of the protractor. Bring in your ruler in centimeters, not inches. And because it's 50 newtons, 1 centimeter equals 300. So 300 divided by 50 is 6. So we're going to make it 6 long. 6 centimeters long. Okay? You must have an arrowhead at the end. You must have an arrowhead at the end. Okay? Now, a couple of rules. Is everyone going to be exactly 6 centimeters long? Is there anyone that's going to be 5.9 because they're not a very good measurer? Yes, or maybe the ruler's a little bit out. Yes. Here's the rule. You can be out plus or minus, how much do you think? 3 millimeters. 2 centimeters? Plus or minus 3 millimeters. So in other words, if it's 6 centimeters long is how long it's supposed to be, you can be anywhere from 5.7 to 6.3. That's a pretty big window. It's very tip, Lawson, yes. The very tip. In fact, I often suggest to students, don't draw the arrowheads on until you're all done, because it's actually easier to measure without. Okay? So that would be 300 newtons east. So it'd be like 3 marks, 1 for the scale, 1 for the length, and 1 for the angle. Okay? Now I don't have another one right here. I want to do another example. Do you guys have room to do another one? I would like to do another one because my morning class, I felt, you know what, they need another one. So let's try one right here. I'm going to go 250 kilometers per hour at, let's say, 17 degrees east of south. 250 kilometers an hour at 17 degrees east of south. Do you want me to do it, or do you want to try it? I'll try it? Okay, you try it. I'll pause. I'm going to get you started if you're having a little trouble. Draw a reference line. But now, instead of labeling it north, you're going to label it south. And you're going to the east, which is which way? To the right. How far? 17 degrees. So grab a protractor. Right? Put 0 at south and go towards east. How far? 17 degrees. Okay? It doesn't matter how long it is, you're just making a little mark. You're marking 17 degrees. Right? And then you're getting rid of that protractor. Now, here's the mistake that students always make. They start drawing from the bottom, when in this case you should be drawing from the top, because that's where I measured from, right? See that? And I will be honest, occasionally I mess up and make that mistake too, so it's easy to do. So you're drawing from the top here. Okay, we're going to go 250 kilometers an hour. Now, I don't have a scale yet, do I? Always start with 1 centimeter equals. Always, always, always. What number shall I use? 1 centimeter equals? 50? Sure. Can you say 1 centimeter equals 50 kilometers per hour? One is a distance, centimeters, and one is a velocity. The answer is yes. This is a scale model. 1 centimeter of paper represents 50 kilometers per hour. So 250 divided by 50 is 5. Get your ruler and connect those two spots with a 5 centimeter long. Okay, so like so. Nope, some people like that. Jaden just asked, can we start like this? If you want to do that for your reference line, by all means, go for it. Do it. It makes people feel better. Do it if you want. You don't have to. You just got to give me something to measure from. Okay? Something to measure from. Okay? All right, so now you've got 4 to try here. Usually we start having difficulties about part C. So I'm going to give you a few minutes to try, and then I'll give you some answers. Go ahead and try. I'm just going to walk you through the steps again, all right? Because I've answered a few questions, and that's been good. I've had lots of good questions. No one said, I don't get all this stuff. So that tells me that you were at least paying attention most of the time. So 25 kilometers at 30 degrees west of north. West of north. Draw a line that points north. West of north. West of north is to the left. How far? 30 degrees. Protractor. Put 0 at north. Like so, and we're going to go 30 degrees west of north, 10, 20, 30 degrees right there, right? 10, 20, 30 degrees right there. And now comes the scale part. So you need something like 1 centimeter equals. Now I had a couple people ask, does it matter what scale I use? No, you could say 1 centimeter equals 5 kilometers. You could say 1 centimeter equals 10. You can say 1 centimeter equals 25 if you want, and then your line would only be 1 centimeter long, right? But that's pretty short, so we want a little longer than that. So 1 centimeter equals, let's go, 5 kilometers. Every centimeter of line represents 5 kilometers. I need 25 of them, so I need 5 and 5 and 5 and 5 and 5. I need 5 5s. 5 centimeters. 25 divided by 5. I need 5 centimeters long. Just a second. Let me finish here. Well, let me finish this one. Okay, let me finish this one because people are watching here. Okay, so I'm drawing from the bottom. Watch, you guys. Watch. Try not to be distracted. 30 degrees west of north, right? And I'm going to be 5 centimeters long. So now, actually, in my case here, it's not long enough, right? Okay, so what am I going to do? I'm going to start at 6, like so. and I'm going to go all the way to the mark, but I'm only going to go to 1. Okay? Like so. Oops, that's the wrong thing. Okay? So just like that. Is that good? Yeah? Okay, not a lot of time left. Try these, please, for tomorrow. I'm going to show you the answers tomorrow. Hold on, don't pack up. I got to give you a couple hints. Notice that part C says 45 N. Does the N stand for north? No. Newtons. Above the horizontal. It doesn't matter whether it's left or right. Try those 3 for tomorrow, please. B, C, and D.